Okay, atomic structure 6, talking about valence electrons. And very simply, though, valence electrons are the electrons in the last energy level of an electron, of an atom. Now, it's not exactly that, though. There are some differences, which I'll go over. So let's get a clean page going here. So when we're talking about non-transition metals, every other element but transition metals, you can follow the rule that in the last energy level, in the last level, last orbital, last shell, the number of electrons in that last shell will be the valence electron. So let me show you a picture of that. So here's calcium. It's an alkaline earth metal, and we talked about them. And you can see in its last shell, its last energy level, and make sure let's review that energy levels. Remember, so we have it starts with K, L, M, N, and it keeps going, and the energy levels get higher as you go up. So the first shell, K, can only hold the S subshells. And the S can only hold 2, no matter what. Now, anytime you see those blue, they can only be 2, no more, well, they could be 1, but they can't be more than 2. And the P's can only be up to 6, maximum. Right? They could be less, but the maximum is 6. And the D subshells would be 10, and you can see that there is a pattern. It's going up by 4. So when we see the F's, if you don't see a calcium, it'll be 14. Again, this is the max they can be. So if we look at the L shell, you can see we have 2, right? 2 S subshells. And then let's count the P subshells. 1, 2, 3, 4, 5, 6. That's the max there could be. Right? So when we look, again, this is a review. In the K shell, there's only S, which gives us a maximum of 2. Now you could have 1, right? Like hydrogen has 1 subshell. That's all it has. Now in the L, the next energy level, it could have S plus P only. So S is 2, P is 6, so you can have a maximum of 8. And you have to go to the next level, right? The M level, which can have S plus P plus D. So we have 2 plus 4, plus 6. 2 plus 6 plus 10, which has a maximum of 18. We can fit 18 within this level, and so on if you just keep doing the math, remember. So when we're talking about non-transition metals, they follow this rule that in the last number, the last 2 electrons in the subshells here, in the highest energy levels, will be the valence electrons. So calcium's valence electrons are 2, because there's 2. And it's also extremely important to know that electrons aren't these particles. They're not these little round balls that are orbiting like planets would orbit the sun. They're not doing that. We're just doing this. We're showing us Bohr model, which is very easy to teach, right? So, but they're not. They're not these particles. In quantum mechanics, everything is different. It's very strange. So they're actually more like waves. But we'll talk about those in much later videos. So again, if we see this definition here, it's not exactly true with transition metals. So an electron in the outermost shell, this last shell, its highest energy level, the number of electrons you see will be its valence electron. In the case of this right over here, you see it has 1. But this is not exactly true for transition metals. So if we look at the periodic table here, let's just draw the transition metals. So I'll use red. Why not? Using red. So from scandium here, we'll just make a little box. This box I'm making are the transition metals. And they follow a little different rules when you want to know how many valence electrons they have. So from scandium all the way to zinc over here. But if we look at the non-transition elements, right, we have the number increases from left to right. So hydrogen will have 1 valence electron in all the alkalis. The alkaline earth metals have 2, and then you go all the way over here to boron, 3, 4, 5, 6, 7, 8, right? So these noble gases all have 8. They're all complete. That's why since they have 8 and they are complete, they don't react, right? The noble gases do not react. We'll talk about noble gases in other videos. Now, in the transition metals, the rules aren't so clear-cut. So let's talk about the transition metals. And we'll start with scandium, since here's scandium over here. Way over here. Now, if you look at scandium's last orbital, its last energy level, you see two s subshells, and you would think that the scandium's valence is 2. There's actually 3. Let me explain why. So it's 3. 3 is the valence electrons for scandium, because in simple terms, though, you have to include the d subshell. You have to include the d subshell when it's not complete. As you can see, it's not complete. You can fit more D subshells in here. Remember, you can always fit 2 S subshells, 6 P subshells, and 10 D subshells. So you can fit 9 more. And because of that, you have to include the D subshell with the S subshell in that other energy level. So until there are 10, until there is 10 of these D subshells, we're not going to add another P subshell in the other energy level. I know it sounds confusing, but this is for transition metals. Just remember very simply right now is that if you see a D orbital, include that in the valence electrons. So let's show another picture. All right, so here's titanium. How many valence electrons would titanium have? Well, it has 4, right? It has, got our pen going over here. Right, so we have 1, 2, and we have the 2 D subshells. We're not including the P, just the D for valence only. So with titanium now it has 2, but like we said, we can fit 10, so we can put 8 more. So titanium's valence electrons are 4. So if we're looking at scandium, it seems to be following a rule, right? Because we'll stick with red, I guess. Right, so it has 3 valences. Titanium has 4, and it'll increase. Except there is some controversy about it. So zinc either has 12 or it has 2, and I'll explain that in a minute there. But if we follow this 12, then again we had 1, 2, but boron has 3. So there's not 13. Then we have 4 for carbon, nitrogen, oxygen, fluorine, and helium in those families. So everyone in that, if you look at this column here, in this family, in this group, they will all share the same amount of valence electrons. But let's go back to zinc for a minute. Let me show you zinc. Now, some scientists, some chemists will actually say that zinc only has 2 valence electrons because the D subshells are complete. So let's look at that, see if they're complete. And others would say, well, you add those that are complete. So if we say 2, that's just these 1, 2 subshells. But look at the D's. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So remember, 2 for S, 6 for P, 10 for D. The D subshells are complete. So some chemists might say that since they're complete, we only include the 2 S subshells in the highest energy level. And remember, the energy levels go higher as you go up. But then others would say, no, you always include the D's, so that's why we get 12. So you might hear 2 from some teachers, 12 from other teachers. The consensus right now, though, is most people will say with transition metals, it's hard to determine exactly. But with gallium, now gallium is right next to, so let's count it over here. Right after zinc is gallium, but gallium is not a metal. So how many valence electrons do you think it has? Well, it only has 3. So the D's are complete, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The D's are complete. So once the D's are complete, then you can add another subshell P finally to that high energy level. So once the P is added, we don't include the D's anymore. So that's why gallium has 3 right next to zinc. Let's show it. Right, and here's zinc over there. There's gallium. Gallium wants to come back. Right, so we have our zinc and we have our gallium over here. So gallium has 3 because it's in the same group of boron, and so on. Now the next topic now is what we show electron dot diagrams. So let me show you those. All right, so here's zinc. So the electron dot diagram, let's get our pen going. It's supposed to show the amount of valence electrons it has. That's all it has. And you can see right here the controversy. Some scientists say 12, but others say 2. You see a lot of dot diagrams of zinc with 2 valence electrons. So again, the electron dot diagrams show how many valence electrons it has, the element has. All right, and here's a few to look at. So you see hydrogen. Hydrogen has 1. How do I know? It has 1 dot. There's a 1 dot there. Let's get that pen going. Right, so here's hydrogen. It has 1 dot, so it has 1 valence. Calcium has 2. Aluminium or aluminum has 3, and so on. So the dot diagrams tell you how many valence electrons are in each element. Now over here we have compounds. We're going to talk about compounds soon. And so you don't see 6 over here. Oxygen has 6. But why do you see 4? Because oxygen, when you're dealing with compounds, and compounds are 2 or more elements coming together, they're sharing electrons. So electrons sharing 2 of its electrons. Same with hydrogen and oxygen over here. This is water. The hydrogen monoxide is another fancy name for water. So instead of seeing 6, you see 4 because oxygen is sharing 2 electrons. So we are going to cover compounds and molecules and bonding very shortly in the upcoming videos. But those are valence electrons and electron dot diagrams for today.